So what we know about magnetism so far kind of boils down to this. Forces QV cross B on a single charge. Forces IL cross B, where I is a vector. Magnitude is equal to the current, L equal to the length of the segment, and B the magnetic field. And the connection between this and this is easy to understand. If you understand the conduction model, then it's easy to understand how this becomes this. That the QV, you add up all the QVs, get a length, you get the current times the length. Okay. So I'll leave it to you to use the conduction model to understand that. And then we have some results. You have MB squared over R equals magnitude of QVB. You have to understand the conditions for this. And you maybe understand it better if you could see the board. If you happen to be looking at the video. Yeah, the camera's totally out of focus. So still out of focus. Oh, there we go. If you threaten it with the remote, it'll go into focus. Okay. Usually. The condition here is you've got a charge moving in some plane, and you got a magnetic field perpendicular to the plane. Then the charge, assuming it maintains its speed, okay, assuming in other words, there's nothing to slow it down, except maybe the magnetic field. Well, the magnetic field isn't going to slow it down because magnetic field being perpendicular to the plane of motion means that the force exerted on this thing is perpendicular to its direction of motion. So that'll create a centripetal force, but it won't create a force with any tangential component, meaning that there's no change in its velocity, only change in its direction. And the radius of the resulting curvature, because things are going to move in a circle because of this. Okay, assuming constant velocity, constant magnetic field, particle's going to move in a circle of radius r. Okay, particle has mass m. So we derived that. We talked a lot about it. So that's what we have there. Also, you got like V equals E over B. Well, that's not a general formula. That applies to a specific case where you have an electric field typically created by two capacitor plates with equal and opposite charges, creating a uniform electric field and a uniform magnetic field and a velocity perpendicular to the magnetic field. And then implicitly perpendicularly the electric field in the same direction as the force on the charge. Okay. Gives you a force that balances the magnetic force and doesn't deflect the particle. Particle maintains a straight line. And if the particle does maintain a straight line in this situation, then you know its velocity. If you know E and B, well, you create B by putting a known current through some coils, Helmholtz coils like we saw, and an electric field by creating a field between two plates, okay? So there we have it. And so there's specific situations here and here. You got to understand what those situations are. You don't just pull that formula out and apply it to something that doesn't entail that situation. So I'll just say, that these apply to specific situations. For specific situations. Is always the case. It's just the basis of what goes on in these situations and other situations involving electric and magnetic fields. Okay, now, important thing about magnetism, okay? In studying electrostatics, you have dipoles, and you've seen the expressions for the field of a dipole. Hopefully you've worked with those expressions. Okay, dipole just consists of two equal and opposite charges separated by some distance. A dipole has a direction, okay? It's the vector, in the direction of the vector, it separates them, and it interacts in ways that you've hopefully seen. You have magnetic dipoles, like a bar magnet acts a lot like a dipole. Or the ceramic magnets, you know, they're flat. I should have one within reach. Just not quite within reach. They're always laying around. Okay. So you got a ceramic magnet here. Okay. And we know what that looks like. And the field comes out of one side and kind of goes into the other side. So magnetic field, and magnetic field follows loops like we illustrated last time. This thing is like a bunch of positive and negative magnetic poles. Okay, it's like, okay, magnetic pole. Positive magnetic, we'll quote that as charge, and a negative. That results in a field that has the familiar shape. Okay. That magnet can be thought of as, see if I can halfway illustrate this. So here's your ceramic magnet. It's like you've got a bunch of, I'll use a plus here and a minus here. They're a little small, you probably can't really see it. It's like you got a bunch of pluses here and a bunch of minuses here. And each of these creates its field. And they all go together. And these are distributed, throughout. So the whole thing creates a field. So the whole thing creates a field that isn't exactly the same shape as this, because it's a combination of a bunch of fields that are shaped like this over 2 dimensions into 3-dimensional space. But it still gives you a field that kind of has this shape, except near the ends where the field gets a little weird. And you can see the illustrations in your book. Okay, so these are magnetic dipoles. I'd say it's a field like the sum of infinitely many magnetic dipoles. It actually is the sum of infinitely many magnetic dipoles. And as we see, And I think it's not until the next chapter, so I'm not going to mention it yet. But a magnetic dipole comes about by a circular loop or some kind of a current loop. So you got a current running around this loop. And we haven't talked about the sources of current. Okay, that's what we talk about next week. And the integrals you use to get this and all that stuff. That's what creates magnetic fields. That's usually, electrons and atoms that are aligned to have magnetic moments and all that stuff. So we're going to talk about magnetic moments. We're not yet going to talk about the electric field of the loop, okay? Except to say that it's equivalent to a dipole. Okay, so this little loop creates a field, again, creates a magnetic field that looks like this, but rotate this around in 3 dimensions. And you see what the field of a dipole would look like, of a current loop. And it would be totally equivalent to the field of a dipole, a plus and a minus magnetic charge. Okay. Now, one difference between magnetism and electricity, electrostatics specifically, is that there are no separated positive and negative charge. You can't separate positive magnetic charge from negative magnetic charge. Okay. So this is like two monopoles creating your magnetic field. I call it a B field. That's pretty common. Okay, pretty common terminology. But probably ain't so, because nobody's ever observed a single positive or negative magnetic charge. Nobody's ever observed a magnetic monopole. You get electric monopoles, electrons and electric monopoles. So it's a proton, basically. Okay, until you get down into the finer structure. I say, but probably ain't so, because probably ain't no monopoles, to put it in formal scientific language. Okay, and you got to say it like that, like you're at a big conference and presenting really high level research. You got to talk the right way. Okay, so since there probably ain't no monopoles, they always occur in pairs. So total magnetic quote charge in any region of space is 0. Since you always have a negative with a positive, you can't have a total charge. You can't separate it. You can't do a magnetic capacitor. Okay, you can't have a magnetic pole current. Okay, can't do any of the stuff you do with electricity, except that Gauss's law still applies. So magnetic flux through any closed surface is zero, because by Gauss's law, the flux of whatever charge you have through the surface is total flux is always equal to the amount of charge you contain within that surface. And unlike for electric field, electric charges, you can't contain any charge within a surface, any net charge. The positive and negative is always equal, always occur in equal quantities. It always occurs in dipoles, never in monopoles. So you summarize that. You know, interestingly, within a quarter mile of my house, back, yeah, I taught some physics courses for Emory and Henry back in the late 80s, I think. Okay. It turns out that the physics professor there, and we're buddies, lived like I could hit a golf ball from my front yard to his apartment. At that time, I might not have quite that distance now. I haven't hit a golf ball in 12 years. Yeah, try to take it easy on. Okay. Used to be able to hit a long way. Probably still can more or less. But yeah, as I slowly leave my youth, things change. Yeah, I've always been tempted. Every summer I get tempted, but I never have time to go out to practice driving range. I have to do it, yeah, every few days for a couple of weeks to loosen up, and then see what happens. I still got the time. And not sure I can still fix the club up. But do that. Okay, anyhow, he lived up the road. And the outgoing professor lived, okay, he lived there, outgoing professor lived there, less than a quarter mile away. And then guy that was mowing the lawn across, or not mowing the field, you know, a few acres across the way. I finally got to talking to him stuff. He's always pretty busy, but you know, it turned out we had a lot in common. He has a master's degree in physics from Stanford. Stanford's, you know, up there at the top echelon of schools. Okay, you know, my school is near the top echelon. There's a big difference between near top echelon and at top echelon. This guy's really smart, but he's in real estate. He's not doing physics. Okay, he did it for a while. And he said he was at Myrtle Beach, I think. There's a guy with an MIT shirt on. And he walked up to the guy and he said, del dot B equals 0, right? Okay. And then the MIT guy was surprised, but yeah. So they talked to him. You know, the young guy and an old guy, so they hang out or anything. So I just said del dot B equals 0. That's a long story to emphasize. Okay. Divergence of the magnetic field is 0. I hope that's not that divergence, just chalk is a little sticky. A little too low. That's a 0 divergence. So you ought to relate that to what you know about multivariable calculus, this and this. Okay? There's a lot of insight involved. I'll say something else. I'm going to say it on camera. It'll sound like I'm bragging or something. I got nothing to brag about, but Okay, brief anecdotes aside, the idea is, again, ain't no monopoles. Okay, so magnetic flux through any closed surface is zero, which is equivalent to saying in differential form del dot B equals zero, which is one of the four Maxwell's equations. Okay, Coulomb's law is another one. That leaves you only two. And their other two are related to all this stuff. Okay. And yeah, one of them is if you integrate the magnetic field around a wire, okay, it's related in a very specific way to the current through the wire. Well, that's really magnetic or electric flux. But it's a flux that's created by this. And you can work out the details of that relationship. You got another one, Maxwell's laws. Okay. But the easiest one is the one my buddy across the road. I mean, like 20 feet from my front yard. This is single, fairly narrow 2-lane road there. And the del dot B equals zero thing. Okay. Yeah, I guess that's all I'm going to say about that right now. Okay. So let's look at something we mentioned last time, which is the effect of magnetic field on a square loop. Okay. Remember, if the loop is oriented like this, so the square is like so, and the magnetic field is this way, then you have a force QV cross B or IL cross B here. Now, if the current's going this way, magnetic field's down, well, I got to turn my hand around. You got a force in this direction. You go down to the bottom of this loop, and now the force is in this direction. So the loop tends to rotate. Now, once the loop is horizontal, those forces are inward. Okay. And the forces over here are inward. So your loop has no torque. So you don't increase its rotation, but if you got good bearings, it's got some momentum from here. So it gets down to here. Okay. And now where are the forces? Yeah, what are the forces? Okay. So you want to think through that. As it's going to turn out, the torque, that towel just didn't want to come out quite. It's a pretty good towel. That's that one. Okay. Torque equals your moment, magnetic moment across your magnetic field. Okay. Now let me make sure I've got that in the right notation. It's blurry anyway, so I'm gonna have to look at it. Hang on a second. Okay, the camera's still being started, so I'm gonna show the picture. That's better. I'll leave the picture up there until I write a little bit more. Okay. Now, what's this mu thing? Okay. Well, from multivariable calculus, you got a fairly simple concept. If you've got a loop with a current in it, okay, you got a current I, you got a loop, then the magnitude of mu, which is called your magnetic moment, is I times the area. Okay. pretty much it. Except you have to know the direction, and the direction is, by the right-hand rule, is your unit normal. Okay. And by the right-hand rule, that's the direction of your unit normal. This means that if you've got a magnetic field in whatever direction, so here's your magnetic field, maybe. Okay, where this is some angle, theta. You do mu cross B, and you get your torque. Okay, well, mu and B are in a plane, and your torque is perpendicular to that plane. A little hard to draw it up here, but you can say, okay, so here's your force, or here's your torque. And it's perpendicular to this, and it's perpendicular to this. Now that is a little easier. The way the torque comes about is, again, fairly easy to understand. If you've got a rectangular loop. Okay, so here's your loop, here's your current. And here's an axis of rotation. If your magnetic field is downward, then again, as we saw, I cross B gives you a force here. And a force here. Okay. Your torque well, put some dimensions on this. If this distance here is, I don't want to use L, now I've got to think of a okay, we'll just say A. Okay, this distance here is A. I don't know what your book uses. I didn't really look at their derivation. Okay, I think they did one. But okay, so your torque has a magnitude of what? Well, this force is acting at a moment arm of A over 2, right? So it's that's the torque on the top, and the torque on the bottom is F times A in this case. And the direction of the torque by the right-hand rule is that way. Okay, so your torque is in this direction. That's the direction in which the angular velocity of this thing changes. Okay, Because angular velocity, if you're rotating around a circle here, your angular velocity by the right-hand rule is that way. So whatever that way means, yeah, an angular acceleration in this direction. Okay. Direction in which your angular velocity is changing, which is what I hope I said a minute ago. So there's the direction of your torque. Now you got to understand torque. You got to go back to your first semester physics to understand the vectors. And then first semester stuff we did at the very beginning of the year with rotating beams and stuff like that, and directions of your angular velocity and angular acceleration. Okay. And how that comes into torque, which is just basically your force times your moment arm. Intuitive concept. If you're trying to loosen a really tough nut with a wrench and you can't turn it, you take a piece of iron pipe, put it in the end of the wrench and increase your moment arm. Exert the same force, you get more torque, and hopefully the thing turns before it breaks. Okay. That should be, you know, working on a car, you know, working on whatever. So, or motorcycle. Nobody likes motorcycles, do they? Okay. Another anecdote. One of my students was talking at the beginning of class about this guy in a motorcycle, and he had a cup full of ball bearings. If somebody's following him too closely, he'd start tossing them. Okay. I understand the impulse, but that's a good way to get yourself killed. You know, you do that to the wrong person. Also a good way to, you know, it's illegal. You go to jail for that. Okay. Even though it's justified as heck to an extent, it's kind of overkill. Although that guy's trying to kill you, although he doesn't know it. Okay. There's a limit to how much you can defend yourself. Not when I'm being tailgated, limits are off. Okay. And I'm ready to take them on, even though they cheat. They carry weapons, they're bigger than I am, they're younger than I am, and they have skills that I don't. Okay. Doesn't matter. I'm kind of stupid that way. Fortunately, I've learned to temper that. It's probably why I've had slightly high blood pressure for most of my life, because I keep holding that in. Okay. Too many people around, even smaller people who are way tougher than I am. I once got tied up for 30 minutes during a ponding in my fraternity. I lived for pondings. I loved them. Wrestling and fighting. You got a bunch of guys carrying somebody over their head or carrying somebody a half mile down to the pond, and you lurk behind a bush and you run out and you dump, you know, you bring the whole pile down. You lock arms with that guy if he's more or less equal in strength and tenacity, and they can't move you. So you hold the whole thing up as long as you can. Like 110-pound wrestler. You know, he was a conference champion in his weight class. His arms are about this big around. I was pretty strong. Okay. Take 15 pounds of this and put it up here. Tied me up. Could have hurt me, but he had enough respect. I was a senior, he was a freshman. And I think he maybe did want to hurt me because he's in love with my girlfriend. And there were torques involved. And I could break anything he had me in, and he'd tell me exactly what he was going to do next, and there's nothing I could do about it. I wasn't quick enough. So anyhow, I don't care who you're throwing ball bearings at, you can't trust them to be wimpier than you are. Okay, well, watch for little guys, they'll tear you up. Okay. Big guys, you kind of know what you're up against. It's not good, but I could go on with stories about that, but we're doing physics. Okay, so you got torques. Okay. The guy could have torqued my arm off me. 110 pounds at the right moment arm and stuff, hanging on you. You know, if it's hanging on you the wrong way, you can't stand up. Okay. I think that's what it's worth. It was, I didn't really need the lesson, but it was an important lesson. You just don't pick on people unless you're ready for the consequences. Okay. So here's your torque. Now, what I'm going to establish here is that this torque is your current times the area of this thing. Okay, because your force is I times L. Oh, ILB, right? So I probably shouldn't use A because I want to use capital A for area. But little a means just this dimension, right? And now if this is the length here, then this equals ILB times little a. Okay. And it's IB times L times little a, right? What's the significance of L times little a here? It's the area of that rectangle. Now you can worry about the vector aspects of this, but in this case, your normal vector to this loop, well, current's in this direction, so your normal vector is out here. So here's your normal vector. So your vector torque, okay, well, ILB times A is equal to mu B if the magnitude of mu is IA, right? Easy enough. It's a pretty easy model, but you got to understand torques and directions and all that stuff. So your vector torque, I say, should be mu cross B. Well, your torque is the vector mu cross your magnetic field, which in this case, in this limited case, is IA times your normal vector, which is kind of obscured down here. I wrote it clearly, but then I messed it up with my diagram. But it's IA times M cross B, right? And what's N cross B? N's in this direction, B is this direction. So N cross B is here, direction of your torque. So there's your vector torque. Which is U cross B. So let's consider where magnetic fields come from, which is basically in electrons spinning around nuclei, although they don't really spin We're not going to get into that problem, okay? They don't really orbit. It's a quantum mechanical thing, but they act like they do, okay? So let's consider I'll put quotes around the orbiting because they really don't orbit, but they act like they do, at least for this model. Okay, orbiting. The proton at 5.29 times 10 to the negative 11th meters. Now, by quantum mechanics, that is the distance at which an electron would, quote, orbit a single proton at its closest possible proximity. You can work out by setting Coulomb attraction equal to centripetal force, how fast the electron would have to be moving, okay? We're not going to do that, and I don't remember what the speed should be. I can work it out, then I'd have to do it in my head and I get it wrong anyway, okay? But let's assume a million meters per second, or orbital speed. So this thing moving a million meters per second at a distance of 52 trillionths of a meter from a proton. So the question is, your magnitude of mu is I times A. Now, if the electron's going around in this direction, then the magnetic field will be up. It's going to be perpendicular one way or the other to the orientation of that loop, to the plane of the loop, right? Now, it's going to look like something I drew earlier. You know, you got a loop and you got the field coming out of the loop, right? Like a dipole. This is a dipole. Okay. So what's the current? Well, the question is how much charge passes a given point in that orbit per unit of time. Now, how much charge? Well, it's that electron passing that thing an inconceivably large number of times every second. So how long does it take that electron to pass a given point in its, quote, orbit? Here's how fast it's moving. Here's the radius of the orbit. Go ahead and work that out real quickly. We spent a little time on this. The idea is if something is moving around a circle at 20 meters per second, that's what we use, okay? So if you're moving around a circle at 20 meters per second, not 10 to the 6 meters per second, that's number 2, big do match, okay? And it's the Helmholtz coils, which have a radius of 10 centimeters, okay? Meaning that the circumference is a little over 60 centimeters, okay? yeah, about 61.6 centimeters, I think. But it is multiplied 20 by pi, right? Yeah, 6.28, 62.8. I'm sorry, that's wrong there. That's what it is. I'm not going to mess with it. Okay, so 62.8, and you can't argue with that. Okay, so about 60 centimeters. It's got to go about 60 centimeters every time it passes a point. The question is how many times it passes a point. And I got answers like, well, you multiply 0.6 by 20. That doesn't make sense because if it was a bigger circle, you'd get a bigger result. But if it's a bigger circle moving at that speed, it doesn't go as many times. Then we got, well, let's divide the 0.6 by 20. And that gives you a small number. Obviously, if this thing's moving 20 meters every second, it's going to go 0.6 meters more than one time in a second, not 0.03 times in a second. Okay. Then I thought, okay, let's unroll that circle. And let's make that circle, let's pretend the circle's 20 meters long, just to give us an easy number. I'm sorry. Let's unroll the circle so it's 0.6 meters long, and we got to go 20 meters. How many times do we do that 0.6 meters in 20? And then we broke it down. Well, if it's 10 meters and you're going 2 meters each time, how many of these would there be in that 10 meters and 20 meters? And this thing was 10 meters. You say, well, 5 times. Well, you got to do that. Okay, you don't want to rely on formulas because you divide the wrong way, which most people want it to do, or you multiply, and the units don't work out either way. Okay, another way to see it. The only way the units work out is if you divide how far you go in a second by how far it is around the circle. Okay, now there's an unimaginably, these things are moving unimaginably fast in an unimaginably small circle, so you've got to get a really big number. Okay. And that big number tells you how many electron charges pass a point every second. And of course, the electron charge is 1.6 times 10 to the negative 19th coulombs. So you're going to multiply that by how many times it passes in a second to get the current, which you then multiply by the area to get magnetic, or the magnetic moment. Okay. The magnitude of the magnetic moment. And of course, it's oriented perpendicular to the loop. And this is directly related to why magnetic materials are magnetic. Because in a magnetic material, if you impose a magnetic field on it, these fields, okay, these atoms are scattered randomly in random directions, okay? And you get no net magnetic field. If you can align them a little bit, then you get a magnetic field. And that's an idea you want to think about when you're talking about the magnetic field of a ceramic magnet, or a bar magnet, an iron magnet, a lodestone, whatever. Okay? So that's what we're moving toward here. So I think I can convince you that, excuse me, I've got to move these boards I'll be tripping over. Should have known better than to put them there in the first place. In the heat of the battle. I was trying to get a bunch of intermediate algebra students to respect the distributive law. Okay, and they're doing it. They're doing it. I think we got there. Okay, so here. Okay, I'm gonna say the radius of the orbit is approximately 5. We won't worry about the 0.29, which is rounded off anyway. So let's just round it off to 5 so we have easy numbers to work with. So the circumference is about, badly written, about 3 times 10 to the negative 10th meters. Okay, which is about 10 to the negative 11th feet, coincidentally, but we're not worried about that. Okay, circumference is about this. Speed. And remember, that's not really how fast the electron orbits. You can set centripetal force equal to Coulomb force and figure out the speed. It's an easy calculation. Numbers aren't particularly intuitive, but it's an easy calculation. So I'll say it like this: the electron passes with frequency speed divided by how far it has to go, which equals then and it's not 10 to the negative 6 meters per second, it's 10 to the 6 meters per second. Moving fast. It's not just calling it a micron per second. Okay, I wrote it right there. My head was used to write negatives after this one, so it just did. Okay. This is going to be about 3 times 10 to the 15th per second. Okay. And that's 3 times 10 to the 15th electron charges per second. As far as current's concerned, doesn't matter, it's the same electron. That's how many electrons are passing every point. Okay, or how many times the one electron passes that point, doesn't make any difference. That's the current. Or three times 10 to the 15th electrons per second times coulombs per electron, 1.6 times 10 to the negative 19th. Got a muscle memory for having written numbers. If I write a 6 here, I want to write a 6 there. If I write a minus here, I want to write a minus there. And that's about comes out about half a milliamp. If we could somehow hook that up to one of our meters here, we'd be able to easily measure it. Okay, on the milliamp meter, we'd get a deflection about like that. Okay. So there we have it. Now that's the current. You got to multiply that by the area. I don't have a lot of area in there, so you get a really small magnetic moment. But that's a little surprising. You get that much current. And of course, if you calculate the force between the electron and the proton, you get a force that you would feel. Okay. And you would easily feel it. You'd actually have to resist it. Okay. Wouldn't tax your strength. But you can work that out, just coulombs law. Both charges are 1.6 times 10 to the negative 19th coulombs. Your separations 0.529 times 10 to the negative 11th meters, or 0.529 angstroms, an angstrom being 10 to the negative 10th meters. And K being 9 times 10 to the 9th newton meters squared per coulomb squared, okay? And you get more force than you would think. It's something that small. Okay, well, now what's the magnetic moment? The area. Okay, well, if you square 5 times 10 to the negative 11th, you get 2.5 times 10 to the negative 21st. And then you multiply that by 3, you get 0.75. It actually comes out closer to 0.78. And that's an easy calculation. And I'm pretty sure that comes out. Oh, wait a minute, it's 5 times 10 to the negative 11, that'd be 25 times 10 to the negative, yeah, 2.5 times 10 to the negative 21st. 3 times 2.5, 7.5, which actually, if you use a little more, a couple digits of pi, it's like 0.78, okay? Which rounds out, it's 2.5 times pi is about 7.8. I keep saying 0.78. Which is about 8. Anyhow, there's your area. So use approximately 4 times 10 to the negative 24th amp meters. So now you can figure out the torque exerted on that single atom by a given magnetic field, 0.03 Tesla or whatever. Okay. Then 0.03 Tesla at whatever angle, relative angle you have. So you have these magnetic moments of your atoms. They're in random orientations. If you can even slightly align a chunk of stuff. So the magnetic moment becomes very significant. And the chunk becomes what we call in highfalutin language a magnet. Okay. Make sense? Halfway. That's basically what magnets are. They have different ways of aligning things. That's pretty easy. If you got a chunk of iron and impose a magnetic field on it, that aligns the magnetic domains. Okay. Your iron, the magnetic moments in the vicinity of a given point will tend to align. Okay. So you got a little grain of aligned magnetic fields. Okay. Somewhat aligned magnetic fields, and then another little grain. And those grains are all, each grain is the result of some kind of alignment. And you get the Ising model or Ising, not sure how that's pronounced, ISING model. And it doesn't really explain that, but it's pretty neat. You get little magnetic domains, and you can get them to at least slightly align by putting a magnetic field around it. For example, by running a current through a loop, which creates an electromagnet. Okay. So you can control the field of the electromagnet. Or you just have any old magnet and you can align it. And you should be familiar, I don't know if you've ever done it, if you got a compass and the red end points north, well, if you bring this into the vicinity of the magnet and you do it with the right end and take it away, the red will now point south because you just reversed the direction of the magnetic alignment in that needle. Okay. So if this doesn't change it, turn it 180 degrees and it will. Very easy to do. We got all kinds of magnets going around. Compasses and magnets. If you didn't do that in junior high science, I don't know why. Magnets aren't expensive, compasses aren't expensive. Why in the world wouldn't you do that? Well, maybe if you're the teacher, you just really want to emphasize biological science. That's great. I love biological science. Every science I had, I loved. And every next one I had, I loved even more, and I ended up with physics. Okay. That's the order they're done in. Great stuff. Okay. And of course, whatever I love is what everybody else should love, right? Everybody knows that, I think. Even though they don't necessarily act like it. Yeah, my wife, for example, no. Medical stuff. And she doesn't like it when I get too mathematical with it. Yeah, I don't like it when she doesn't like it, so, fortunately, I don't mess with her any more than I do with 110-pound wrestlers. So we get along. Interesting debates sometimes. I sent her one last night. What in the world was it about? I saw it in the middle of the night. I was awake for a while. It was really good. Oh yeah, it's how you are really biologically not really yourself you're the set of bacteria in your gut. They have more they do more to your physiology than your physiology does to itself. Pretty interesting. And it's quantified, the rates of this, the rates of that and stuff. So I'm hoping she brings it up again so we can have another intelligent discussion. Which probably end up with me in the hospital. Okay. Okay, what else? Those are two big things. Now there's more. There's the Hall effect, which isn't too hard to understand. You got to shove the material that's got some width. Like think of a, where in the world are they? Oh yeah, I was using those in my kitchen. So they're not here handy. But like, okay, you got one of these things, but you go ahead and straighten it out so it's thin and stuff like that. Now you got current flow and you got electrons drifting this way. Now you got a magnetic field here. What happens to those electrons? They experience a force and magnetic field. Now, if the electrons are going this way, the current's going this way. So you do the magnetic field cross the current, you're going to have a force this way, which means you end up with a greater density of current here than here. Your current density, your J thing, current divided by cross-sectional area, okay, at a given point, is greater here than here. And you can measure that by putting a voltmeter across between here and here, because you got more electrons here than you have here. You have a negative charge here, a positive charge here. Okay, so your voltage drops from this side to this side. So you have a potential difference in this direction. Okay, and that's not hard to measure. We probably won't actually do it, but that's what you call the Hall effect. And there's a formula for it. And you might even want to deconstruct the formula and think about it if you understand the conduction model and charge densities and current densities and all that stuff. So actually, I'm not going to write anything up here, but that's the Hall effect. Let me just take a look at the chapter summary and see if I've forgotten anything so I get wrapped up in things. You do have electric motors, but I'm going to let you read that. And in lab, we'll probably play around with that little loop I showed you last time and see how you get an electric motor out of it. And I did want to do the integral, and might do it next week if you want to look at it. The integral for the total force on a circular loop. It's easy to get the total torque and total forces and stuff on a rectangular loop. On a circular loop, you've got to partition the thing because every part of that loop has a little different direction with respect to the magnetic field. Okay, how does that all sum up into a torque if you've got like an axis through the center of this thing? Okay. So you really want to kind of understand that integral. In the next chapter, we're going to get into a lot of integrals when we talk about source of magnetic field. Okay, because every little increment of this loop also is a source for magnetic field. So this thing has a magnetic field that tends to want to align with the imposed magnetic field by this torque thing. Okay, so it's all pretty neat. Also, tends to really reinforce what you know about multivariable calculus, which then tends to reinforce what you know about physics. Okay.